Hello, Legacy Sabers, Marsh here. So today we're going to be graphing exponential growth and decay graphs. You're going to want your foldable. You're also going to need a calculator today to understand where some of these numbers are coming from so that you can fill in your parent table. Our essential question today, how do I graph an exponential function? So first, I got a question for you. Would you rather have option A, $10,000 given to you every day for the next 30 days, or option B, a penny today, but it will double every day for the next 30 days? Now you're probably thinking, well, Marsh, I probably want $10,000 today. But if you select option B, you're going to get a whole bunch more money all the way at the end compared to option A. Even though it doesn't look like a lot to start with, it is because it is growing at an exponential rate, which means that it is multiplying by itself, which means you're going to get a lot more money than you ever thought possible than that 10,000. So let's talk about exponential growth and decay. There are things in the real world that grow and decay. For example, your bank account interest, that is exponential growth. It grows because you gain money every month or every quarter, depending on how it compounds. Population, that one either could be growth or decay, depending on what you're looking at. So in case of Bismarck, we were growing for a while there exponentially so far. That's why Legacy actually was built, to be honest. Uranium or any kind of radioactive material, that one is a decay function. Depreciation on your car, aka the amount of money your car is worth, that would be a decay. And then also carbon content of fossils. This is how you determine how old a fossil is, because you're determining how much carbon is still in the bones. That would be also a decay, because as the fossils release carbon, you are seeing how much have you decayed from it. So when we're looking at our exponential functions, we have two different kinds of graphs. We have growth graphs and we have exponential decay graphs. So if you're looking over here, looking at this graph, notice it looks from left to right, it looks like it's going up. This would be a good picture of a growth graph, because left to right, it looks like it's going up. From left to right, it looks like it's kind of like a slide going down. That would be a decay graph, because as I go further in my x value, the y value is going down. Now, our parent function for our exponential equation looks like this. Y equals a times b to the x minus h power plus k. Our parent function, unlike the other ones, is going to change each time, because our base b is a different number each time. So we're going to have to find our parent function, and on that same note, our parent table every single time. Now that b, that is the base there, is going to tell you if you have growth or decay. If you have a b that is greater than 1, you have a growth graph. And if your b is between 0 and 1, it is a decay graph. Now be careful. Do not make the assumption that just because you have a fraction, you have a decay graph, because 5/4 is also a fraction, but it is bigger than 1. So be very, very careful to not make that mistake that you see fraction, aka decay. Be very careful with that. So when we use our parent table, we're going to have to create it each and every single time using that parent function as we see it show up. So let's try our very first problem. We want to graph f of x equals 3 times 2 to the power of x. So first thing, my parent function is this guy right here, the 2 to the x. So y equals 2 to the power of x. Now, since my base is bigger than 1, that means my type is going to be a growth graph. Now, I'm going to go and make myself my parent table. So right over here, my parent table, your x's are never going to change. It's going to be the y's you're going to want to change. So we're going to start with -2, -1, 0, 1, 2. You're going to want to try all of some negatives, some positives, and then that 0 in the middle. What I'm going to do is I'm going to take those x values and substitute them in for that exponent. So the first one I'm going to find is 2 to the -2, which, remember, negative exponents means it goes down to the bottom of the fraction. So I would technically have 1 over 2 squared, which would be 1/4. Now, I also understand some of you struggle when it comes to negative exponents. Calculators can definitely tell you what 2 to the -2 is. So feel free, if you need to use your calculator, definitely do that. -1, I need to put that for my exponent. So it's going to be 2 to the -1st. That's just going to flip it around, right, and get us 1/2. 0, I'm going to put 2 to the 0. Anything to the 0 power is 1. Plug in a 1. 2 to the 1st is 2. And then 2 squared is, in fact, 4. So I have my parent table of -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. Now, what I'm going to do is I'm going to do transformation. So this 3, we know that that 3 always multiplied by a number. So we're going to multiply our y's by 3 to get our answer here. So my x's are going to stay the same because we're not changing anything there. But then I'm going to multiply by 3. So 3 times 1/4 is 3/4. 3 times 1/2 is 3/2. 1 times 3 is 3. 3 times 2 is 6. 4 times 3 is 12. So now I have my function. Let's go ahead and graph it. So -2, 3/4, -1, 3/2, 0, 3, 1, 6, 6, and then 2, 12 is going to go off the graph, so we're just going to put it up there. Now, notice this function. If you kept on going backwards on your x value, so like let's say we picked -10 for an x, we would get 2 to the -10th, which is a tiny, tiny decimal. What you're going to find is that this function is going to have an asymptote. And that asymptote normally is at y equals 0, right down here. But it does move up and down, depending if your function moved up and down. So I'm going to want to always draw in my asymptote so that when I draw my function here, it draws a beautiful little line for me. So my asymptote, since it didn't move up and down, we're going to get y equals 0. And then domain and range, well, I can go forever to the left and forever to the right. So I got -infinity to infinity. But my range, since I have that asymptote at y equals 0, I have to say I can go to 0 but not include it, so parenthesis there, to infinity because I go forever up. Let's try the next one. So my parent function, again, just the guy to the x. So it's going to be y equals 1/5 to the x power. And since 1/5 is between 0 and 1, this is going to be a decay graph. So now let's go ahead and make ourselves our parent table. So our x's, same thing, -2, -1, 0, 1, 2. And then 1/5 to the -2nd would be 25, because we're going to flip that thing around. 1/5 to the -1 is 5. 1/5 to the 0, 1. 1/5 to the 1st, and then 1/5 to the 2nd. Now, looking at my parent or my transformations, it looks like I have a +1 on the outside, not included with that x. This is an up and down move. So that means I have to add 1 to all of my y's and go ahead and fill in my new table. Adding all those 1s. Ooh, 1 and 1/5, 1 and 1/25. That's a fun number. -2, 26, all the way up there. -1, 6, 1, 2, 3, 4, 5, 6. 0, 2, 1 and 1/5, 1 and 1/25. Do you notice how this graph looks like it's going down closer and closer and closer and closer to 1, but it's not actually including 1. So what you're going to find, being that we moved up, you're also going to find that you're going to move up on the asymptote. So I'm just going to go like this. Graph my graph here. So my asymptote moved up to y equals 1 because I shifted vertically. So I'm going to get an asymptote at y equals 1 this time because I shifted up. My domain, left to right, now looking at it, notice there's no problems in our domain. So we're still going to have negative infinity to infinity on that. Notice both of these functions have had that, and yes, you're correct. All exponential functions will have that for a domain. So that is the easiest part of this entire probably graphs of these. My range, my asymptote did move up, so I do have to put a 1, but we're not including the asymptote. That's why we have a parenthesis there, to infinity for our function there. Now, let's try the worst kind of problem that could show up. Let's find our parent function. Now notice we don't want that plus 1 right here. It's just 2 to the x. So we're going to take that plus 1. That's going to be a transformation that we're going to be looking at. So let's go ahead and find our parent table using -2, -1, 0, 1, 2, those same x's we've used the last couple of times. And I'm going to plug in my numbers here to get all my y's. Now, all of the transformations are in play here. So we got a minus in the front, so that's going to change all of your y's to be negative. So I'm going to do all of the negatives here. Now I need to multiply all of my y's by 1/4. This plus 1, notice how it's attached to the x. That is going to be a horizontal shift, and it's going to be opposite of what we see. So just because we see a plus 1, we actually have to do -1, so we have to go to the left. That's why we're going to subtract there. And then I'm going to add 3 to my y's. Oof, this is going to be a very interesting parent table here, guys. Those y's are going to be disgusting. I'm going to do my x's first. Okay. -1/4 times a fourth is -1/16. And adding that, ooh, Marcia's going to need a calculator. Let's use a calculator quick. We're going to get 47/16, which Marsh has the decimal equivalent. 2.9375. Marsh's going to use a decimal just because I don't know what 47/16 looks like. And then we're going to multiply. We're going to do the next one. So negative. Nope. Marsh pushed the right buttons. She made sure she did negatives there. Times, find my next number. $2.875. -1 times a fourth is a -4 plus 3 is 2.75. Can kind of do these numbers now. -2 times a fourth is -1/2 plus 3 is 2.5. And -1/4 times a fourth is -1 plus 3. That is 2. All right, let's graph here. So -3, 2.9375. Well, that's right below 3, right? -2, 2.875. You're like, Marsh, that's barely the difference. I know. Trust me, guys. These are kind of disgusting when you're looking at all of your answers here because literally they're almost all very close. Now, this one's kind of hard to see because with this function, notice it's negative. So what you're going to have, and instead of climbing to the right positive, you're going to actually climb to the right negative. So this graph is going to be a growth graph, but it's going to be reflected. So it's actually going to look like this. Now, in your head, you're probably looking at it and going, Marsh, no, that's a decay graph. Actually, no, it's a growth graph, but it's growing negatively. So a good example of this kind of graph would be a graph that shows the U.S. debt. it is growing negatively, but nevertheless, it is growing. We're going to have our asymptote. Notice we got really, really close to 3, right? So we're going to have our asymptote at y equals 3 right here. So we're going to fill this in. So this is still a growth graph. Even though it doesn't look like growth, it is growth because it's growing negatively. Y equals 3. Our domain, still that negative infinity to infinity. And our range, negative infinity to 3, but not including 3, of course. Now, there exists a really fun number that is also an exponential, and he is called E. E stands for Euler's number, and I know that does not look right. You're like, that's not how you say that, but it actually is Euler's. That's how you pronounce that. And E is equal to 2.718, so 2.72, something around there. E is irrational. It can't be written as a fraction. It's kind of like pi. What we find is that as the value of math gets really close, if you do 1 plus 1 over n to the n power, you get really, 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 really close to E. E was found when they realized that if you make it so that your bank account compounds continuously, so you never stop compounding, you will find that you actually get really, really close to this value. And that is where this number was born in real life situations. Now, we can graph E, which is kind of a neat idea. So our parent function would just be y equals e to the x. So we're going to have to write ourselves a parent table. Now, our x values, no different here. Oh, also, being E is just 2.72. That's bigger than 1, so this would be a growth graph, right? Now, I'm going to have to use my calculator. Now, on your calculator, you're going to find E most likely on the LN button. So you're probably going to have to find the LN button, and above that, usually for the second key, you'll see an E to the x. So I have to push on my calculator second LN, and then it will pop up an E. So I'm going to type e to the negative 2, and we're going to get a number of 0.14, 0.135, but I'm going to round. Now I'm going to do the same thing. I'm going to type e to the negative first. E to the first, or e to the 0, is 1. E to the first is 2.72. Oop. There we go. Sorry, guys. Tablet decided to be weird there. And then e squared is a total of 7.39. Now, if you're having trouble finding that e on your calculator, please talk to me so I can help you find it. Usually it's just hiding somewhere as a second key. So now I got to do my transformations. I got to add 3 to my x's, and I'm going to add 2 to my y's. So we're going to get 1, 2, 3, 4, 5, 2.14, 2.37, 3, 4.72, and 9.39. So let's graph those. 1.2, that, that one, and then right there. So notice, normally, again, our asymptote would be at y equals 0, but it's been shifted up 2 because our entire function shifted up 2. So I'm going to have y equals 2 there, and I'm going to draw that in so I can connect my dots. There we go. So my asymptote, like we said, y equals 2. Domain, everything, all reals. Range, from 2 to infinity. And our last function of the night, I'm going to get you started, and then I'm going to have you guys try this one on your own, since this video has been super long already. Now, notice there's a negative right here. Now, we've never seen a negative in an exponent before, but all we know that that does is it just changes the base, right? It makes it a fraction. So if I have e to the negative x, technically I can just rewrite this problem as 1 over e to the x minus 2. So that means your parent function is going to be 1 over e to the x. That means when you type it into your calculator, you're going to want to see and find what is 1 over e, and then type in your numbers. Now this type of graph, because 1 over e is a fraction that is less than 1, you're actually going to get a decay function on our picture. And then once you find your parent table, you're going to want to shift down 2. So I'll let you try this one on your own, and we will check it when we get back to class. And with that, that is the end of this video. I will see you later, Sabers.